Our tool for this cosmic adventure is a Python library known as Pygame. Pygame allows us to create a window into our virtual universe and bring planetary motion to life. Now in this code, it's like the heartbeat of our simulation, where we set up the window size 800 by 800 pixels and define our planet's color like white, yellow, blue, red, and dark gray. Let's define a planet class in Python to simulate the motion of celestial bodies in space. Each planet is initialized with parameters such as position, radius, color, and mass. The simulation includes the calculation of gravitational force between planets, updating their position over time, and display their orbits and distance from the Sun. But what's powering the scale of our celestial dance? Enter the astronomical unit, or AU. 1 AU is the average distance between the Earth and the Sun. The gravitational constant G is a key factor in Newton's law of universal gravitation, which describes the force between two masses. Now let's take a look at this. G is the gravitational constant, m1 is the Earth mass, m2 as the Moon mass, and r² is the distance between Earth and Moon. The x and y screen coordinates for the object are calculated based on its coordinates self.x and self.y, and the scaling factor self.scale. The addition of width over 2 and height over 2 centers the object on the screen. If the object has more than 2 points in its orbit, it updates and scales the orbit points and draw lines connect them on the window using pygame.draw.line. The attraction method encapsulates the gravitational interaction between celestial bodies. Given another celestial body, it calculates the force component in the x and y directions. The method considers the distance between the bodies, updates the distance to the Sun if applicable, and employs Newton's law of universal gravitation to determine the force. This encapsulation allows for a clean separation of concerns, focusing on the physics of gravitational attraction. Now the update position, this function is like the planets adjusting their dance moves based on how much they attract to each other. Each planet feels the pull from its cosmic buddies, adds all those pulls, and decides how to groove next. It's like saying, feeling the pull from my paws, time to update my dance routine and keep the celestial party going. So let's bring everything we have done. Our celestial bodies represented by instance of the planet class interact gravitationally and move in the window. The main loop updates positions, redraws the window, and responds to user events. Initialization includes setting up the Sun and 4 planets, each with specific properties. Now the grand finale, let's play our code. And ladies and gentlemen, that's the result of our solar system simulation. Thank you for watching. As comets strike and asteroids soar, the cosmos hums an eternal lore. In this cosmic ballad, a spectrogram witness the wonders of the celestial band. Now as the stars fade and galaxies shift, in this cosmic journey a celestial gift, with awe in my eyes as the universe lifts. My name is Lucas and this was Solar 50.